So today we are going to start the next topic, that is red black trees, right? So we'll start with the introduction, then we'll be learning about the operations that we do in the red black trees, that is insertion and deletion. See, basically, we have seen, we have been studying the binary search trees. Then we had discussed about the AVL trees. AVL trees are used to balance the binary search trees, because in the real world we cannot control the input data that we receive, and we have to. And when we receive any kind of input data, the structure of the tree can be in any of the forms. So it may be highly unbalanced, it may be balanced, and it may be skewed, right? So when we receive these structures, and we are creating the binary search tree for using the binary search tree data structure for storing the data. So in that case, we need to balance that particular tree so that we are able to do the various operations in the O log n running time. So that is the main goal behind the balancing of these trees that we have discussed. So the first strategy that we have discussed, or the algorithm that we have discussed for the balancing of the tree, is the ABL tree, right? So in the ABL tree, we have been, what we have been doing to balance the binary search tree. We have been performing the various rotations, like either single rotations or the double rotations. And after the double rotations or the single rotations, we were trying to ensure that the tree is balanced with a balance factor of 1, and so that we are able to get the guaranteed O log n running time. So red black tree is another type of data structure that is also used to balance the binary search trees. But along with the other information that we store in the nodes, the extra information that is stored in the nodes is the color, which can be red or black only. So there are two colors which can be used, that is either red or black. And height is of the order of OH, and which is of the order of O log n, where n is the number of nodes in the red black trees. So in the red black trees, the most important thing that we have to focus on is the properties of the red black trees. And everything, that all the operations that we will be doing, they revolve around satisfying these properties. If any of these properties is violated, that means it is not a red black tree. So we can say that a tree is will be called as a red black tree only if all these four properties are satisfied. That means when you make any insertion operation or your deletion operation, any kind of operation you do, if any of these properties is violated, so that means it is not a red black tree. Then in order to make a red black tree, you have to work in that direction, so that like you have to do certain kind of operations. You can say we do the coloring, we do the rotations, to in order to ensure that these properties are satisfied, and the tree, after insertion or after deletion, it again becomes a red black tree. So the four properties, you can note it down. You have to cram these properties by heart, so that you can do any of the operations. And even while discussing the various things, that the operations I'm going to discuss, you should remember, otherwise you won't be able to understand even a single thing, a single concept in the red black trees. So you should know these properties by heart. So every node is either red or black. That is fine. That will be there, right? So important thing is that root is always black. Root cannot be red, right? So this is an important property. Most of the time, like these first two properties are not violated, right? Because root is the first node to be created, so we can color it black. And all the nodes will be either red or black. So first two properties are not violated most of the time. The property which is violated, that is case number 3. So if a node is red, then both its children are black. So most of the time this is the property that is violated, and we have to work in the direction so that this property is not violated, and we have to take all the measures in order to work on that, and the tree becomes a red black tree. So if we say a node is red, then both the children are black. So that also means if a node is black, that means it can have any children. It can have a black children also. It can have a red children also. But if the node is a red node, then it cannot have a red children. It has to mandatorily, you can say compulsorily, have a both the children as the black nodes. Then the fourth property is, for each node, all paths from the node to the descendant leaves contain the same number of black nodes. So this is called as the black height that we are going to discuss next. So that means whenever you are doing any kind of operations, you have to ensure that the black height of the node that should be same for all the leaf nodes. So all the paths from node have the same black height. So most of the time you can say that either the property 3 or the property 4, they are violated, and we have to work in the direction so that these properties are retained in the tree, and we can call that tree as the red black tree. So let us see this particular tree. This is, we call it as a red black tree. So here you can see the root node is black. So the circle around that number, that is called, you can say we have used this coloring scheme in order to indicate that the root your node is a black node or a red node. So the red circle indicates the root, it is a red node, and the black circle indicates it is a black node. So the root is black. So the first property you can see written, every node is either red or black. That is fine. All nodes are either red or black, and there are no other colors. Second property is the root and leaves are black. So here you can see here for all the leaf nodes that we were considering, they are called as the last nodes, and for every node we have created these sentinel nodes, we call them, and they are written as nil, and these are also given the colors, and the color of these nil nodes is a black color. So these, you can say the structure of nil is same as the normal nodes, but only thing is, if they are not storing any value, they are storing the nil. But any all other you can say, because if we are taking the structure of the nil node same as the other nodes, you may be storing some other data also along with that. So that may be any kind of data you can store in the nil node, because we are more concerned or you can say we are more interested in the value of that is stored as nil. So nil of t, you can say, to represent all the nil nodes at the leaf. So these are called as the sentinels. Basically, they are used earlier also we had used to indicate that we have reached to the end of the tree. So here also they are used. These we are using these sentinels, and even if they are not given, you have to assume them that they are there. It may be that in the further trees I may not have shown the nil in the as the leaf nodes, but they are there. You have to imagine that that is all there. Okay, so we say nil of t has the same fields as the as I just told you, the ordinary node, but its color is black. So all the nil nodes, they are of black color, and the other fields may be set any kind of values that is up to you. So here you can say the red node is having the children both the black, as you see, if a node is red, the third property says if a node is red, then its both children are black. And for each node, all paths from the node to descendant leaves contain the same black number of black nodes. So whether you let us say we start look at the nil node from the bottom, and then we start looking at on the path from 26, 41, 47, 50. So here you can say we have two black nodes, right? Then we see another path 26 to 17, we have two black nodes. 26, 41, 30, we have two black nodes. 26, 41, 47, sorry, 26, 41, 30, 38, we have two black nodes. So here you can see on every path we have two black nodes. That means fourth property is also satisfied. That means we can say this tree is a red black tree. So next we move on to black height of a tree. So black height, if we have to tell the black height of a node, of a particular node. So here we had considered the black height of the tree from with respect to the leaf nodes. Now we let us see the black height of a particular node. So if let us say if the current node that we are considering is 26, then the black height of this node will be counted on the basis of the number, except this node, how many black nodes are there. And in this category, we will also be counting the leaf nodes, that is the sentinel nodes, which are also the black nodes. So here you see the count of that. So the height of the node we consider that is equal to the number of edges in the longest path to the leaf. So the number of edges in this particular path are 4. from 26 to 41 to 47 to 50. That is the longest path it has. So and its height is height of this node is equal to 4, and black height is equal to 2. So except the 26th node we are counting, except 26, here you can see the one node black is 47 and another is the nil node, that is also black. So for every node we can count the black height, that is for 41 BH is equal to again 2, for 47 it is 1, then for 50 also it is 1. So for 17 it is 1, then 30 black height is equal to 1, and for 38 also the black height is equal to 1. So this is how we compute the height of the node as well as the black height of the node. So black height of the node we require because this is one of the important properties of the red black tree that we have to maintain in order to call a particular tree as a red black tree. So we say the red black tree with n number of internal nodes will have a height of at most the maximum height that you can say the red black tree can have is equal to 2 log of n plus 1. So that we say that height is less than equal to twice of log of n plus 1.